That should be on. Okay. Thank you. So yes, I'm going to be talking today about population 3 star formation and what seems to be the first steps towards a new picture of how this actually works. I want to start by thanking my collaborators. I'm not going to name them all because there's an increasingly long list of people involved in this project. So I'm going to start by just briefly going over what, up until a couple of years ago, I would say, was really the consensus view of how population 3 stars formed. So in this figure, which is from Abelbrand and Norman 2002, this top panel shows the development of structure in the dark matter. So we start at a high redshift with very little structure, but then by a redshift of about 20, you've formed nonlinear structures, mass scales around 10 to the 5, 10 to the 6 solar masses. If you look at what the gas is doing, that falls into these dark matter mini halos, virializes, and then collapses to increasing density in the center of these halos. If you look at the temperature, the gas out in the IGM is very cold. Once it falls into this mini halo, it virializes, shocks up to, in this case, around 1,000 Kelvin, and then cools in the center through H2, line emission, reheats somewhat, and eventually you can follow the collapse all the way down to stellar scales. So this is another example from a different simulation where you're starting on the scale of a single dark matter mini halo and you're zooming all the way down to scales of a few AU. With most of these simulations, if you follow the collapse, you did not see evidence for fragmentation. You could basically just zoom in and zoom in and zoom in. The gas didn't break up into multiple fragments. You can follow it all the way down to essentially the scale of a protostar, and so the natural conclusion to come to is that, okay, this halo is just going to form one star. Now, at the point at which you form a protostar in this type of calculation, its mass is very small, and typically you have the initial protostar having a mass of maybe 1/100th of a solar mass, but it's surrounded by a very large amount of gas, which is all falling in under the influence of gravity. So if you assume just a fair fraction of that is going to be accreted by the protostar, and accreted rapidly because the temperatures are high, then you predict that the final protostellar mass is going to be large. So there's a considerable amount of uncertainty, even in this picture, about what that final stellar mass is going to be. But even the most pessimistic, optimistic, depending on your point of view, estimates put the mass scale of POP3 stars in this picture at least 20 solar masses. So you're basically going to form very massive objects in this way. But, as Avi talked about this morning, we're starting to see something of a paradigm shift. There's an increasing number of simulations which are now showing evidence for fragmentation. One of these, this work by Turk, Arbel, and O'Shea, this actually does see the gas breaking up into a binary system during this initial collapse. They basically looked at a large number of realizations of this kind of POP3 star formation in mini halos and found in about 20% of cases you could actually form two objects rather than a single object. But most of the work has been driven by a new generation of simulations which make use of an important technical improvement. So most of this earlier work was limited by the fact that once you collapse to very small scales, once you've formed a protostar, the time step in your simulation gets extremely short. You're basically limited to the Coulomb time step, and the Coulomb time step on the scale of a protostar is basically of the order of a day. So if you then want to evolve the system for hundreds of thousands of years, it's obviously completely impractical. But what we've seen over the past couple of years is a new generation of simulations which use a technique called, basically, we refer to this in SPH as sync particles, and you can, in a grid code, you can talk about sync cells. The fundamental idea is you replace the regions that you can't resolve, where the time steps get very, very short, with some artificial sync particle or sync cell, which represents that gas And that allows you to evolve beyond the formation of the first object. And what we've found is that the previous conclusions that you don't form fragments really seems to be because you're just looking at the very first fragment to form. And that if you can just get beyond the formation of this first object, you start to see more evidence for fragmentation. So one of the first studies to see this was also in Avi's talk this morning, is this work by Stacey, Greif and Brom, who were looking at disk formation and fragmentation on fairly large scales with limited resolution. I'm mostly going to be talking today about some more recent work that zooms into much smaller scales with higher resolution and looks in more detail at the physics that's going on in these scales. So I'm going to start by talking about some work that we published recently in Science. The basic idea of this simulation, we start with cosmological initial conditions with relatively high mass resolution. Then we take the final output of this cosmological simulation on the smallest scale on which we still got resolution. We then resample these initial conditions and do a second simulation starting from basically the end point of this large-scale cosmological simulation. So we do this to generate this kind of initial condition on a 10 parsec scale, then resample this with much higher mass resolution and follow the further collapse of the gas. I will skip past that because that's just talking about the physics included. I don't have unlimited time. Basically what we find, if you follow the collapse of the gas to very small scales, to begin with, everything looks like it does in the standard picture. You form a protostar somewhere in the middle of this object. Then we create a sinc particle to represent this protostar, so we're not limited by the Coulomb condition to take very small steps. We can actually take time steps that are of the orders of years rather than days. If we follow the further evolution of the gas, we find that it starts to build up this disk around our central protostar. So this red dot is the central protostar. We build up a disk. We're looking in this sort of images down onto the disk plane. The disk develops spiral arms. Basically, it becomes gravitationally unstable. It starts having to transfer angular momentum through gravitational instabilities, and eventually these spiral arms actually start to break up and form stars. And only a few hundred years after the formation of our first protostar, we've already broken this disk up into multiple objects. The disk forms stars basically because it becomes gravitationally unstable. If we look at this Q parameter, the two-way stability parameter, we see that while very close to the central object, Q is very large. Once we come out to a few tens of AU, we drop down to Q values below 1, which indicates instability. And we also have a high H2 fraction throughout this disk, which means that the gas can still cool effectively. The reason we build up such a massive disk is simply because gas is accreting onto the disk faster than it can be processed onto the star. So this is a somewhat complicated figure. So what we're showing here is, with the black line, this is the rate at which material is moving through the disk, so along the midplane of the disk towards the star. So if we look at, say, 100 AU, gas is flowing radially inwards at that point in the disk at a rate of about 0.01 solar masses per year. But then this blue dashed line here shows the rate at which the gas is raining onto the disk at that radius. So we see that basically throughout the disk is gaining mass by accretion from the envelope faster than it's able to transfer this gas onto the central star. This basically means that the disk just gets bigger and bigger and bigger, and at some point it becomes gravitationally unstable. In this plot, I'm showing the main thermodynamic processes that are operating in the disk. And this is looking at the parcel of gas that ultimately forms the second protostar in our simulations. So The protostar formation in this case actually happens at t equals 20. This is starting with t equals 0 to some arbitrary point. So at these times, the gas is still in the disk. It's not yet gone into the gravitationally unstable part of the spiral arm, and our cooling is dominated by, it's that blue line here, by H2 collision-induced emission. So this is an H2 cooling process that really kicks in about 10 to the 14, 10 to the 15 particles per cc. It's essentially the inverse process to collision-induced absorption, which I think is probably more familiar to people here. And at this point, the main heating process is essentially just compressional work being done on the gas in the disk. As this parcel of gas collapses up to much higher densities, though, we see H2 formation and H2 dissociation become far more important. I'm not sure how clear it is to the folk in the audience, but there's actually two lines here. So the H2 formation heating is this red line, and then there's a blue line showing H2 dissociation cooling. So it's actually the difference between these two that leads to a net change in the thermal energy of the gas. And H2 dissociation in this collapsing clump of gas is able to provide enough of a heat sink to allow it to remain cool. So to allow our gravitationally unstable clump to collapse up to high densities. More recently, we've done a couple of follow-up studies to this work. So the first of these is on the archive. It's a paper by Greif et al. So in this study, we're using a different hydrodynamical treatment, a code called a repo. So our previous work was done with smooth particle hydrodynamics. A repo is a different type of code. It's still a Lagrangian code, so it's still one where our resolution elements follow the fluid, but it's actually a grid-based Lagrangian code. The important thing to note here is it should have rather different numerical artifacts, numerical systematics than SPH. In this study, as well as using a different hydrodynamical treatment, we're looking at more than one mini-halo. In the Clark et al. Study I was just talking about, we only looked at one object. Maybe there was something really weird about that object. So in this study, we're looking at multiple different objects. And we're using two different models for treating sink particles. So a kind of standard treatment in which they don't really merge, and something that we can call sticky sinks, where whenever two sink particles come close together, we merge them into a single object. The main result of the Greif et al. Study, we still see fragmentation. We see fragmentation in every single case. So here are 3 of the 5 halos we look at. In this study, we were also able to run for a longer time. So the picture of the disk I was showing you earlier would only run up to a few hundred years. Now in this study, we can run out to 1,000 years. And we're still seeing the same basic pattern of events. We form a disk, that disk starts breaking up into fragments, and once you've formed a bunch of fragments, then the evolution gets very chaotic. Again, we see this dashed line is the total amount of mass in protostars, and we show the rate at which the individual objects are gaining mass. So we start out with just 1 or 2 things. So I mean, this blue line in each case is the object that forms first, but then after a few hundred years, we start forming more and more fragments. And the accretion onto these fragments, so this is looking at the mean accretion rate and the total accretion rate of our collection of protostars, starts becoming more and more random, basically because the evolution of the gas starts becoming very chaotic. These are the mass functions of the sink particles we form in these simulations at, I think, a time of about 1,000 years. So these will not be the final mass distributions of stars, but they do possibly give us some hint of what that might look like. So we're looking at the 5 different halos here, and then we've just combined them all into a single sum. And there's 2 the results of two different simulations plotted for each of these. So they're just the plain coloured bars in the histogram are from our simulation with standard sink particles, and the ones with stripes are when we're using these sticky sinks. So we see that our first kind of approximation to treating sink merging and kind of maybe doing something slightly more accurate with close encounters between these sink particles tends to push the mass distribution up to slightly higher masses. But we still, even in this case, we still have a lot of objects with masses of only a solar mass or less. So this is quite different from what you might have expected based on the previous arguments that all POP3 stars were going to be very massive. It's only 1,000 years. The other thing to note, however, is we are seeing, I mean, these mass functions are very flat. So what we see in simulations of present-day star formation, we tend to see mass functions which are power laws. So there's the standard saltpeter power law IMF with a slope of about minus 1.3, 1.4. That's not what we see here. These look flat. And what that means is that most of the mass, in this case, is still in these most massive objects. So although we have this tail of low mass objects, in some respects it's not so different from what we were seeing before, because we're still putting most of our mass into massive stars. It's just we're now seeing these low mass stars forming along with the massive stars. We can also look at the, well, start to speculate about the fates of these objects. So this is a plot showing position versus velocity of all of the sink particles in one of our halos at the end of the simulation. So this is with standard sink particles, and this is with sticky sink particles. So the effect of using these sticky sink particles is basically we don't have any objects left with very small separations, because they all merge. It's only the things that manage to form a long way away from each other that survive as isolated objects. If we, rather than just looking at plain old velocities, if we look at the velocity compared to the escape velocity of the region simulated, we see that many of these sinks are, well, have velocities that are well below the escape velocity. It's quite likely, if we follow the simulation for longer, that many of these objects will merge. But there are also some objects which have velocities significantly above the escape velocity. They've undergone some close encounter with another sink particle, and they've been flung out of the system. And these objects, I mean, assuming we're treating these close encounters correctly, and that's something I'll come back to, these objects are going to escape from the center of our halo. They're probably not going to accrete very much more matter, and so they're going to retain the masses that they have at this point. And so this gives you a mechanism for actually, even though we're looking at a fairly early time in the simulation, if we have low mass stars up in this portion of the plot, they're probably going to stay at low mass, even though we don't know what's going to happen with all the low mass stars down here. In another follow-up study, so this is work by Round Smith and collaborators, we're using this, looking at the same set of halos as in the study I've just talked about. We're using somewhat lower resolution to allow us to run to even longer times. And the main point of this study was to look at the effect of accretion luminosity heating. So basically the idea is when these protostars accrete gas from their surroundings, they have to radiate away the gravitational binding energy of this gas. Most of the binding energy is released basically as the gas falls within, or from within a couple of protostellar radii onto the protostar. If you just think about GM over R, well, GM squared over R. Most of the energy comes out once you're very close to the protostar. So the luminosity of these accreting protostars can be quite high. This is going to heat up their surroundings, and what we wanted to see is, well, does this suppress fragmentation? Can this actually change what I've been saying? And basically, the answer is no. So this is one of the plots from this study, just looking at one halo going out for a few thousand years, and this is with including the effects of accretion luminosity, and we still see fragmentation. And in this plot, we're comparing the rate at which sinks are forming in a simulation which does not have accretion luminosity included, so that's this dashed line, with the rate at which we form them when we do account for the accretion luminosity, and that gives you the red line. So we see that for some of the mini halos we're looking at, there's very little difference, and for some we do see suppression of fragmentation. But in no cases do we see complete suppression. We always form some fragments. And now also, in these simulations, we're now running up to a time of 10,000 years. And the main reason we're stopping at this point is because in all of these simulations, by a time of 10,000 years, we formed one star that's already 10 or 15 solar masses, that would already be reaching the main sequence and therefore starting to emit large amounts of photodissociating photoionizing radiation, and that's something we currently can't treat. So given some means to treat that in the simulation, and that's something we're working on right now, I don't think there are too many technical challenges standing in the way of pushing to much longer timescales and really getting a better sense of what the final mass distribution of objects is going to be. I'm running out of time, so let's just skip ahead to the atomic physics bit. There are several major uncertainties. Close encounters of the fragments. When we're using sync particles, we're basically doing one of two things. In this kind of standard treatment, they're just treated as point masses, scatter as point masses. This is certainly the wrong thing to do, because the protostars represented by these sync particles are not point masses. I mean, they're big fluffy balls of gas. When they come close to each other, there's going to be all sorts of tidal interactions between them. They're probably going to lose energy in encounters. They may well have a high probability of merging. We've made a first attempt to treat that with this kind of sticky sync particle algorithm, but we really need a much better idea of what's going to go on in these close encounters, because as I showed you, this does make quite a difference to the distribution of sync particles, how many of them are going to get flung out of the system. We need to look at the much longer term evolution. I've just talked about that. Treat the effects of H2 photodissociation and photoionization, which is something we're working on right now. But finally, we are limited to some extent by uncertainties in the input physics. And the main uncertainty I want to talk about now, and I'll just spend a couple of minutes on this because I know we have talks later in this workshop about this, is the uncertainty in the rate of three-body H2 formation, specifically in the rate of the hydrogen plus hydrogen plus hydrogen giving H2 plus H reaction. So this is a plot I drew up a few years ago, which just compares the different values for this rate coefficient I was able to find in the literature. We're interested in its value at a temperature of about 1,000 Kelvin, so somewhere between 500 and 1,000. So if you look at the scatter in the rates available in the literature, we're talking about a factor of 1,000 uncertainty in this rate coefficient, which, yeah, by anyone's standards, a factor of 1,000 uncertainty is pretty large. So last year we finally finished up a study looking at the effects of this uncertainty. This is work done in collaboration with Matt Turk and Tom Arvell. And so what I'm showing in this series of panels is a comparison between three different simulations using different values for this rate coefficient. So this top set of panels uses the fairly small value that was used in Abel, Bryan, and Norman. The middle set uses somewhat larger value from Pallas, Operative, and Stahler. And the bottom set of panels uses the largest value in the literature, which is from a paper by Flower and Harris from a few years ago. So these first three panels show the density of the system as we zoom into smaller and smaller scales. And you can see immediately that with the Abel, Bryan, and Norman rate, we get a very spherical looking system. The gas is forming H2 through the three-body process at a relatively slow rate. It doesn't cool rapidly. It tends to stay fairly spherical. As we increase the rate at which we're forming H2 through this three-body process, we start seeing far more elongated structures, far more aspherical structures. And it's basically because the gas can form H2 faster, so it can collapse faster. If we look at the temperature distribution on this same scale, we again see we're forming a lot more H2, therefore we're getting colder. That's what's allowing us to collapse. So with the Abel-Browne and Norman rate, we're actually close to isothermal. There are there's a bit hotter in the middle, a bit colder around the edges, but it's mostly isothermal. But as we look at these other rates, we're seeing a far more of a distribution of temperatures. And if we finally just look at the H2 fractions again, with the slow rate, you don't form much H2. You've only got a very small region which is actually fully molecular. By the time we come down and look at the Flower and Harris rate, essentially everything in this panel is fully molecular. So, to summarize, we know that the high accretion rates we see in POP3 star-forming systems lead to the formation of massive disks around POP3 stars. We know that these disks fragment. We can be confident with the simulations up to this point. They form a bunch of sync particles, and assuming that these objects survive as individual protostars, we'll form a small, very dense cluster of stars. And some of these stars will be gravitationally scattered out of the system, and therefore have the possibility of remaining at low mass. We've seen that accretion luminosity can reduce the amount of fragmentation that happens in some cases, but it never completely suppresses it. We don't know what effect ionization and photodissociation feedback will have, but these only kick in once we've already got one star that's already at least 10 or 15 solar masses. And by that time, you've already had a certain amount of time to fragment. And on the atomic and molecular physics side of things, the three-body formation rate and the heating rate associated with that represents one of the major uncertainties in the input physics here. So we have a load of uncertainties associated with how we're running the simulations, which we can hope to improve ourselves just by doing better simulations. But getting a better value for this rate coefficient is something that we really need the experimentalists and theorists in the audience to do something about. Thank you. I mean, on the timescales I've been talking about, the stars are basically all still in the pre-main sequence phase, so nuclear fusion doesn't contribute significantly. That's basically the point at which we're stopping. Is the most massive objects are the first ones to reach the main sequence, and it's when fusion kicks in within those objects, they suddenly get much higher effective temperatures, start producing ionizing radiation. That's the point at which we have to stop, because we can't currently treat that. Right. Yeah, so the question is, well, two questions. What about outflows and what about magnetic fields? We believe outflows are going to play a much less important role in POP3 star formation than they do in present-day star formation, because it's much harder to drive winds from POP3 stars. You don't have the metals, so you don't have the metal ions and the associated lines to push against. You're only going to drive a wind with continuum processes like electron scattering, which means that you've really got to be accreting it very close to the Eddington luminosity for any effect like that to become important. So the general consensus is winds from these stars are not going to be significant. Now, the question of jets really ties in with magnetic fields. And yes, magnetic fields are something I didn't have time to talk about, but it's something we're also studying in our group in Heidelberg. Even if you don't start with a very strong field, it's likely that some form of turbulent dynamo is going to operate during the collapse and generate a stronger field. What's not clear right now is how strong that field is going to be. It's something we're trying to simulate at the moment. I think the models that we've already used to look at this suggest that the magnetic energy is never going to be dominant. That it's always the thermal and kinetic energy are going to dominate. So it could be that even if you can amplify a reasonably strong field, it's not going to change things too much. The other thing is with a turbulent dynamo, you're not building a correlated field. The field is basically, it's only got structure on small scales. If you look at average over very large scales, you have no mean flux. So it's not going to have the same influence as if you were starting with a well-correlated field. But exactly what influence it does have and whether it's going to interfere with this picture of fragmentation is not something we've yet been able to look at. At the moment, we've kind of had two parallel studies, one looking at magnetic fields and one looking at fragmentation, and we really need to merge all of these. So I think, ask me again in 2 years and I'll have a much better answer to your question.
You mentioned that you're now able to simulate for 10,000 years and like to push that to higher numbers. You also showed that the onset of formation of the stellar clusters have more time scales of 100 years. So that tells you that the initial condition is somehow, you can change the initial condition as much as you wish, and you probably will still have a onset. How much does the initial condition supposedly affect your final master sequence of stars?
That's something we'd like to be able to quantify. I don't think we can quantify that yet. I mean, the initial conditions do have a strong effect. Qualitatively, you always see the same thing. You always see fragmentation. But once you've formed a large number of fragments, I mean, you basically have a chaotic n-body system. So if you start it in a slightly different state, it's going to end up in a different state. So I think ultimately this is a question we're going to have to address statistically just by doing very large numbers of realizations. And I mean, you're never going to get exactly the same outcome, but are the trends that we can understand statistically, like things like the final mass function. What we're seeing from the work we've done on the mass function so far is, I mean, we do always seem to see this flat mass function, so we're always tending to be dominated by a few massive objects. And it's likely that is not terribly sensitive to the initial conditions, and that will persist if we look at longer timescales. But right now, I don't really have a good answer to your question. I think we need to do a lot more simulations with better physics as well.
Within the people that do simulations, there is some criticism of this sync particle approach. Maybe you can summarize that in a few words, because there are some people concerned that this numerical approach is not robust, or that will introduce artificial results.
Well, so I think it depends what you're interested in. I mean, sync particles are an ad hoc modification to the equations of fluid dynamics. I need to be upfront about that. So on one level, the question is, well, would you rather do something ad hoc to allow you to study the later evolution, or just stop at some point and then say, well, we can't study the later evolution, so we're going to assume that we know what happens. I think if you're interested in the evolution on scales that are much, much larger than the effective size of the sinks, so all of these sinks have some effective accretion radius, where if gas gets within that radius, we put it into the sink. So on scales significantly larger than that, they're unlikely to have much effect on the flow. On scales very close to the accretion radius, then clearly the fact that you're using this artificial thing is going to affect the outcome. I mean, that's largely what I was talking about with this issue of mergers and close encounters between sinks. We know we're doing the wrong thing there, but right now it's the best thing that we can do, even though it's not as good as you would like. I mean, basically, at these densities, we're not worrying too much about the internal energy levels of the H2 molecules. So we're assuming when we create an H2 molecule, you've got 4.48 eV, all of that's going to go into thermal energy, because, I mean, you're doing this at number densities above 10 to the 8 or 10 to the 9 particles per cc. So the chance of any of that getting radiated away before it's thermalized is fairly small. And similarly, for dissociation, we're assuming that's just removing 4.48 eV from the energy of the gas. I think at the sort of densities, particularly in the disk, which in fact is much higher densities, around 10 to the 14 particles per cc, I think that's reasonable. If you want to treat those effects at much lower densities, so if you're not worried about formation heating from the 3-body process, but from the standard 2-body H-, H2+ routes, then you have to be more careful, because a lot of that binding energy is actually going to get radiated away. Well, I mean, we are attempting to do a simulation without sink particles, where we just let basically use a form of adaptive mesh refinement. So this is actually the refinement that you get in a repo. Just setting some maximum refinement scale, and then that acts as kind of an artificial pressure to stop the gas from collapsing to very, very high densities. So that allows you to potentially simulate these systems without needing to rely on sinks. And so far, the results we're getting from that seem consistent with what we're seeing when we do use the sinks. But those simulations are very, very much slower. So, I mean, so far, we've not run for very long at all. I mean, maybe, I think the last time I talked to Thomas Greif, who's leading this effort, we'd maybe gone for 20 or 30 years after.
Well, it's just like in real time. It takes you a year to simulate 1 year.
It's not quite that bad, but I mean, so yeah, I mean, we are making efforts to address this, and so far we're not seeing anything that looks too different. But I think it's too early to say that we're really going to get the same answer. But yes, clearly, the extent to which we can trust sink particles and the results we're getting from them is one of the major limitations here, as it is in most simulations of present-day star formation.
Thank you very much, Simon.